Hey guys, so today I want to talk about something called the combined gas law. So we have the three gas laws. We have Boyle's law, which is pressure and volume. We have Charles' law, which is volume and temperature. And temperature, remember, we have to deal with in the Kelvin scale, so the absolute zero is 0, and then everything is above that. And then we have Gay-Lussac's law, which is pressure and temperature. Okay, so we have those three gas laws, but the thing is, when we actually have a real situation, you actually have to kind of keep one of those things constant for those three gas laws. So with Boyle's law, pressure and volume are inversely related, but we are making sure that the temperature doesn't change when we deal with Boyle's law. Like, we're not even looking at temperature. So in the real world, all three of these can actually change at the same time. So you're going to have Boyle's law and Charles' law and Gay-Lussac's law kind of all happening at once for a situation, because it's hard to actually keep the temperature the same. So let me show you an example of this. Okay, so I have here a pop bottle, and inside this pop bottle I have a thermometer. Thermometer currently reads, it's about 23 degrees. Okay, about 23 degrees. And then I also have this syringe which has 10 milliliters of air inside of it, and it's sealed. So it is able to actually go up and down, but we're starting off with 10 milliliters of air in there, and this is just where it is. Okay? So this is for measuring volume. This is for measuring temperature. And then I actually have a pump here with a pressure gauge on here. Okay, so right now it's 14.7 in the room, and then I've got this pressure gauge here. So what I'm going to do is I'm going to change all three of them at the same time by just pumping it up. Okay, so I seal it off, and I'm going to attach this. Go ahead and let you watch here. As I pump it, the pressure in there is increasing. You can see the volume of the syringe is decreasing as I do this. It was at 10, and now it's down to about 5. So the pressure went from 14.7, and my pressure gauge here is reading 30, so it's actually 47, or 44.7. Keep going here. All right, it was at 23 degrees, and the thermometer here, I know you won't be able to read it, is actually reading about 29 or 30. Okay, so it's gone up by about 6 degrees. The volume of that syringe has gone down, way down, and then the pressure on here, it's at 40 plus the original 14.7, so it's at 54.7 right now. Okay, so an increase in pressure, decrease in volume, an increase in the temperature. We have all of those laws happening at once. All three of these are changing. Okay. Now, if I take this and I just release the pressure, it'll go back to 14.7. You can see the volume then increases as the pressure decreases, and the temperature is dropping. The thermometer is still going down. It's already down to 25 degrees Celsius, so it's dropping because of that pressure change in there. So we have these laws happening here. Okay, all three of them happening at once. So how do we deal with this mathematically? How do we deal with this by doing the math for it? Let me show you here. We actually have a new equation. This is the new equation for something called the combined gas law. It is all three gas laws combined into one equation. Okay, so we have P1, pressure 1, times V1, volume 1, divided by T1. And this is going to be equal to pressure 2 times volume 2 divided by temperature 2. And all the temperatures have to be in Kelvin again, just like with the other three laws. This is just combining the three laws. And if you look at this equation, you can actually see all three laws in the equation. So for example, if I just erase the temperature, that's Boyle's law right there. That's Boyle's law. Okay? If I erase the volume, that's Gay-Lussac's law. If I erase the pressure, that's Charles's law. So all three laws are actually combined into this equation. Okay, so I have an example problem here for the combined gas law. Let me show you how this works. A sample of nitrogen gas, it's stored in a 500 milliliter flask at 108 kilopascals of pressure and 10 degrees Celsius. Okay, the gas is then transferred to a 750 milliliter flask, so it's got a different volume. And then this new flask is also hotter, it's 21 degrees Celsius. So what is the pressure, the new pressure of this nitrogen gas in the second flask? Okay, so we have our original equation that I just showed you. We have pressure 1 times volume 1 divided by temperature 1 is equal to pressure 2 times volume 2 divided by temperature 2. Okay, so what I'm going to do here is I'm going to look at this and try to identify all of these pieces. Okay, so a sample of nitrogen gas is stored in a 500 milliliter flask. So that's volume, and that's going to be our starting volume. So this right here is V1. Okay, at 108 kilopascals. So if this is V1, then this is the pressure that goes with it. So this is P1, that's a pressure, and 10 degrees Celsius. That would be T1. Okay, so it starts at 10 degrees Celsius. So we have P1, V1, and T1, right? The gas is then transferred, so now we're going to our second part, okay, to a 750 milliliter flask. This would be V2 at 21 degrees Celsius as a temperature, so new temperature, that's T2. What is the pressure of the nitrogen in the second flask? Okay, so I'm going to take these pieces of information and I'm going to put them into this equation. Now, before I do that, I'm going to actually convert these temperatures to Kelvin because they're in Celsius and they have to be in Kelvin in order to do this. So I'm going to add 273 to both of these. So 10 plus 273 is 283 Kelvin. And then this one plus 273 is 294 Kelvin. Okay, so I've converted those into Kelvin. So let me start plugging these in. P1 is 108 kilopascals. Times V1, which is 500.0 milliliters. And I'm including that 0.0 so that I can remember that I get that Sig Fig later. Divided by T1, which is 10 degrees or 283 Kelvin. Equals. Now I go to the other side. P2, I don't know. Okay, that's what it's asking me for. So I'm just going to put that as X times V2, which is 750.0 milliliters, divided by T2, which is 21 degrees Celsius or 294 Kelvin. Okay. First thing I'm going to do is I'm going to simplify this. All right, so I'm going to take it and go 108 times 500 divided by 283. This simplifies to 190.8127208 equals X times and then I'm going to simplify this, 750 divided by 294. .551020408. Okay, so I just simplified these things here. So it's X times the number equals a number, right? Now I want to get X all by itself now. So I'm going to take and try to get rid of this number here, the 2.55 thing. And I'm going to do that by dividing both sides by 2.55 and the rest of it. So divide this by 2.551020408. And that makes it go away over here. So the only thing that's left is X. Okay, so 190.8127208 divided by, it's going to hit second answer, 74.7985 0.86, and that's probably enough sig figs right there to round it. So that is my answer. That is kilopascals, since that's the unit of the original pressure. All right, and if we think about it, the volume actually did increase here quite significantly, so that pressure is going to decrease because of that. But it's not going to decrease all the way as much as it would because the temperature is increasing, so it's actually expanding or increasing that pressure a little. We got both effects happening where the volume makes it decrease, but the temperature makes it increase. Okay, we end up with a lower pressure. So sig figs, that one's got 3, 4, 3, 4, and 3. So I'm going to round this to 3. That's the lowest. 1, 2, and 3. So the 9 rounds it up. 74.8 kilopascals of pressure is our new pressure. Okay, let's do another one. So I have a sample of gas. It has a volume of 2.00 liters and a pressure of 0.750 kilopascals, where its temperature is 25 degrees Celsius. Right? The volume is expanded to 4.0 liters and the pressure is reduced to 0.500 kilopascals. What must the temperature become in order to cause these things? Okay, again, our equation is P1 times V1 divided by T1 equals P2 times V2 divided by T2. Okay, so first I'm going to identify all the pieces. A sample of gas has a volume of 2.0 liters. That's a volume. So this here is V1, starting off volume. And a pressure of 0.750 kilopascals. So that is the same pressure as V1. So this is P1, okay, P1 and V1. And the temperature is 25 degrees Celsius, so that would be T1. Now that is in Celsius, so I'm just going to go ahead and convert that at 273. Gives me 298 Kelvin. Okay. Next, the volume is expanded. Okay, so we're changing the volume. This is now 2. So that is a new volume. This is going to be V2. And the pressure is reduced to 0.500 kilopascals. So that is a new pressure, P2. What must the temperature become? So we are looking for T2. We're looking for T2 here. Okay. So I'm going to take all these numbers now and plug them in. So I've got P1 right here, 0.750 kilopascals, times V1, which is 2.00 liters, divided by T1, which is 298 Kelvin, equals P2, which is 0.500 kilopascals, times V2, which is 4.00 liters, divided by T2. I don't know it, so I'm just going to put an X. Okay? So first thing I'm going to do, simplify. All right? I'm going to simplify this. Get my calculator here. 0.750 times 2.00 divided by 298. This side simplifies to 0.005033557. And it equals 0.5 times 4.0. 2. This is 2 divided by x. Okay? So now that I've simplified it, next step is to get x by itself. Now there's a problem. X is on the bottom. It's a denominator. So I actually don't want to get x by itself. I want to first get it out of under the bottom. Anytime you have x in the bottom, get it out of there. Okay? So I'm going to go ahead and take it and just times both sides by x so it gets out of the bottom here. So what we're left with is 2 on this side, and then this is x times 0.005033557. Okay? Now that x is not in the denominator, now I can get it by itself. I'm going to divide both sides by this number here, 0.005033557. Divide this side by that number, 0.050333557. That makes it go way over here, so the only thing that's left is x. 2 divided by this number. 2 divided by 0.005033557 is 397.333337, and it is Kelvin. Okay, that temperature is in Kelvin because this temperature was in Kelvin. All right. Now I'm going to go ahead and round this. I had 3 Sig Figs, 3 Sig Figs, 3 Sig Figs, 3. So I'm going to round this to 3. We're going to call this 397 Kelvin. Okay. So the new temperature is 397 Kelvin, which if I want to convert that into Celsius, subtract 273. We have 124 degrees Celsius. Okay. And that's how you'd find a temperature, specifically something that's on the bottom in the denominator for it. Okay? Okay, your turn. I want you to pause the video and give this one a try here. Pause the video and give it a try. Okay, you got an answer? So again, we have P1 times V1 over T1 equals P2 times V2 over T2. This right here is P1. This right here is T1. And I'm going to convert that to Kelvin. So add 273 gives me 303 Kelvin. Okay. And then it's got an initial volume of 2.00 liters, so that is V1. If the temperature is raised to 80 degrees Celsius, that is going to be T2, which convert to Kelvin. Add 273 gives me, I can't do that one in my head, 353 Kelvin. Okay, 353 Kelvin. And the pressure is increased to 440 kilopascals. There's P2. What would the new volume be? So V2 is what we're looking for. Okay, so I'm going to take all these numbers and plug them in. We have 110 kilopascals, P1, times our volume, V1, 2.00 liters, divided by T1, which is 303 Kelvin, equals P2, which is 440 kilopascals, times V2, I don't know that, that's what I'm looking for, X, divided by T2, which is 353 Kelvin. Okay, next I'm going to simplify. All right, so, and you can do this however you want. I personally like to simplify and then find X. All right, but you can do this however you want as long as it is correct algebra. So, I'm going to take 110 and times it by 2, divide it by 303. Okay, 110 times 2.00 divided by 303. This gives me 0.72607, 26073 equals, and I'm going to simplify this, 440 divided by 353. 1.246468924 times X. Okay, I'm going to get X all by itself, so I'm going to divide both sides by this number, 1.246, makes it go way over here, and then on this side, divide by 1.246458924. Okay, so the only thing left on this side is X, 0.726072673 divided by, I'm just going to second answer, gives me 0.5825082509. And that would be my new volume in liters. Okay. Now, Sig Figs, looking up here, this has 2, this has 3, this has 3, this has 2, and this has 3. So my answer, 2, both of these have 2. I'm going to round it to 2, next one's a 2. 0.58 liters is my new volume. Because I raised the pressure and raised that temperature. Okay, if I just raised the pressure, it would go down even more than this. I think it would go down to 0.5 liters. But since I raised that temperature, that actually made the volume go up instead of down. So it goes up a little bit. And that is the combined gas law.